Okay, so my name is Elliot Slaughter, and I'm here today to talk about Regent. Regent is a language designed for the Legion programming model. I like to think of it as sort of a refinement to the core Legion ideas. These are all ideas that exist in the C++ API, but they're not always they're not always explicit, and they're not always checked in the C++ API. But it supports a lot of the same concepts. We still have implicit parallelism with explicit sequential semantics determined by the original program order that the code is written in. We still have tasks, which are just functions, and we automatically discover dependencies between tasks based on the arguments which they declare. And so that means, for example, we can take some piece of code which just looks like sequential code and automatically find a dependence graph which tells us how we can execute that code in parallel. And for this language, this is the actual code that we're running. This is not going to be behind some C++ API. And we can also automate the data movement because we understand exactly what data each task needs to use. So if you've used the C++ API before, you're probably familiar with how much code it can take. But for those of you who are new, it can get somewhat verbose. And it's not just that we're using C++. What you have to understand about Legion is that we require you to specify a lot more about what your program is doing. In order for us to find dependencies, we need to know exactly what data each task is going to use. And so there's just a lot more that you have to say. But some of this is stuff that we can actually determine automatically with a compiler. And so what Regent effectively does is that it removes some of those moving parts in order to give you a simpler model with fewer things that you have to think about. And that gives us this nice code on the left instead of the longer code on the right. And the nice thing about the compiler is that we're going to be able to do this while still providing performance which is identical to the code that you would have written directly to the Legion C++ API. Now, there are a lot of other systems that use compilers, and I think it's worth pointing out that this compiler is somewhat different from the other compilers that are automatically parallelizing that you might have seen. And in particular, when we use Legion, we're effectively using a dynamic analysis to discover parallelism. This dynamic analysis has a fundamental overhead because we have to do some work for every single task to determine what it can run in parallel with. And this effectively means that we have some boundary on what we can run, depending on how much overhead there is and how long the tasks are. The goal of the compiler is to effectively help the runtime reduce this analysis cost by moving more of the work into compile time. And so the hope is that with the optimizations that we're going to be able to do, we're going to be able to extend these boundaries to run things either at larger scales or at finer granularity. Some of these things you're going to be able to do by hand, and I'll tell you what those things are as I walk through the optimizations. Some of these things are going to be difficult to do by hand, and you really need a compiler to do them effectively. So I wanted to start by just doing a quick overview of what it looks like when a Regent program runs on the Legion runtime system. Tasks are conceptually sequential, so we can read the code for them effectively top to bottom like they were running in any standard sequential programming language. We start execution at a main task, and typically we start by allocating data. So we have regions, which are just some collections with a set of fields, a set of keys, and some set of fields stored for every key. So they're similar to arrays of structs. We can partition these regions into disjoint subpieces or potentially alias subpieces in order to give us data parallelism. And then we can launch subtasks on the regions or their subpieces in order to decompose the problem into potentially parallel parts. Now, in order to understand where the parallelism is in the system, we need to make sure that we describe what privileges each task has on the regions which it's taking. So a task might read some region or it might write some region, and we can specify exactly what fields it's going to read or write. And in some cases, we can actually discover additional parallelism from those field declarations for tasks that are operating on different fields. Now, if we look at how this executes on the Legion runtime system, what we're going to find is that every task executes effectively in a sequential thread. So we're going to start running this code in some thread. And again, we read the code top to bottom like it's running sequentially. Every time we hit a task launch, we're going to launch a little piece of asynchronous work to a special runtime thread that does some analysis to figure out what that task depends on. So here, because the task A is the first task to be launched, there are no dependencies, and it can start running immediately. And I'm just going to assume that we have enough CPU cores here to run all of these tasks in parallel, but there's a separate mapping phase which gives you the ability to determine where that task is going to run. As we continue running the program, that main task thread is actually just going to go ahead and keep running. And it's going to continue feeding tasks to the runtime, which it's going to do analysis on to determine the dependencies and run as soon as they're ready. So these B tasks are all going to depend on the A task, which means that they can start running as soon as this A task is finished. And then we're going to finish execution with this C task, which depends on everything that came previously. Now, there are some optimizations which I did to this code. This is code running with the compiler's optimizations enabled. And I'm going to get back to that in a little bit and describe exactly what those optimizations are. But I wanted to go and talk in a little bit more detail about the language features so that you can understand what sorts of things you have available to you when you write code in the Regent language. Yeah?
How do you do the resource allocation to the runtime threads and the application threads? Is there some recipe for that, or is it
So you can control how many threads we allocate to the application versus the runtime. Currently, that's a command line flag that we set up sort of at the beginning of the run. I believe in the future, we're going to be working towards more of a configuration system where you can dynamically choose that depending on what the machine looks like.
When you're statically analyzing and running parallel, are you also doing your own alias analysis?
Right. So yeah, so the compiler is going to have its own version of the analysis. It's effectively the static version of the dynamic analysis that we do in the Legion runtime. And because it's static, we're going to be limited by the alias information that we have available to us. You're going to see, actually, in the next talk, how we've designed the system so that we can do a lot of that alias analysis without resorting to traditional techniques. And that's going to give us a lot of power to be able to do this analysis effectively, right?
I'll just add that, I mean, part of the design of the whole region system and the partitioning system is so we can make the alias analysis possible. I mean, Legion and Regent are really designed, you know, if you're a programming languages person, to make alias analysis easy.
Right. So in every Regent program, we typically start by allocating the data. And again, data in Regent is stored in regions. A region is effectively the cross product of a field space and an index space. And field spaces are basically just structs. The syntax looks very similar to what you'd expect to see in C or C++. But you can also do some more interesting things like structs or field spaces which have pointers to other elements in regions. So for example, this is a field space which is going to have a pointer to another node in the region which it takes as an argument. And this is something that we can use to build up, for example, a linked list. Index spaces get allocated dynamically in Regent. This is an index space which is unstructured. So it's an index space over this opaque pointer type, which has no explicit geometric relation to any other element. We're just going to create an empty index space with 28 elements in it. And we can also create structured index spaces which operate on 1 or 2 or 3D rectangles, right? So this is going to create a 2D rectangle that's 4 by 7. And then when we create regions, we're basically just supplying the index space and the field space, which is going to create that cross product which we've seen several times before. Tasks are only one of the operations that we can do on regions. We can do things like fill regions with a value. This first fill is going to fill x, y, and z with zeros. And we can also do things like copies from one region to another. And so these are things that you could write using tasks, but it's usually easier just to use the built-in methods that we've got here. The tasks themselves are, again, effectively functions. Tasks take arguments, which can be regions or index spaces or scalar data types of whatever kind. And tasks declare their privileges on their arguments, specifically on the region arguments, to specify how they're going to use those arguments, whether they read or write the arguments, and what fields they're going to read or write. And in particular, because we've got a language, and because these privileges are declared, we can actually check these privileges at runtime, or at compile time, to throw a compile error if you do something wrong. So if you have a region which you didn't declare privileges on, and then you try to access it, then we'll throw an error for that. And we can call tasks just with a standard function call syntax. We've got a fairly standard set of control constructs. We've got if statements, while loops, for loops over integer ranges. And then we've got a couple of more interesting control constructs like for loops over index spaces. Remember that grid is a two-dimensional index space, so this is effectively equivalent to a 2D loop nest. It's going to iterate over each of the indices in this index space. And we can iterate over pointers in a region. And so this is going to give us all of the nodes in the linked list. And element here is going to be a pointer so that we can modify those elements if we want to. Yeah?
Do those all have implied sequential semantics?
So the first three do. Oh, so the question was whether these have implied sequential semantics or not. The first three do. These if, while, and standard for loops do. The second two have sequential semantics but don't tell you the order that they're going to run in. So it might be useful.
Isn't that the same as they have no sequential semantic? I mean,
But it's not the same as running concurrently, right? Reordering the loop iterations is not the same as having actual concurrency. And so in particular, if your data layout is Fortran array order versus C array order, right? You might have different regions in different array orders. It might be advantageous to run your loop iterations in a different order to match what data layout you've got in a region. And that's a decision we'd like to be able to provide to the mapper so that it doesn't have to be baked into the source code.
right, so I guess the question, well, in particular, they're not for alls, right? I can't do things in arbitrary order, but you're not going to tell me which order I'm going to get. That's coming from the mapper. So as a code author, I have to assume when I write these things that they're all concurrent.
So let's see here. What's the best answer?
Again, if I haven't phrased that well, I mean, what do I have to know as a code author when I write one of these things?
So
I think assuming that it's parallel is a reasonable assumption. Yeah, so I mean that's one way to certainly simplify your life.
Right. You certainly can assume that it's parallel, right? And if you do, and you do things that are only valid if it's running in parallel, then your code will run fine. But it's also sometimes useful to do things which wouldn't work in that context. And you can still write those things with these semantics.
I want to add in one more thing here, which is that Legion and Regent are continually evolving, and one of the things we look for is feedback, like you haven't actually quite said, but are implying here that maybe a different way of doing it would be useful as well. And we're certainly in this case, I'm actually more inclined to agree with you that I would like some way to get a understandably sequential semantics, but I would also like in some cases to be able to give the ability to the mapper to make that a performance choice. And knowing when the two is right clearly needs an extra bit of syntax that we're open to figuring out.
So look, I'll agree with you. I will just observe that one of the issues I found in OpenMP is that the sequential semantics of OpenMP for loops are not exactly well defined. And so it can be difficult to programmer to reason or understand what dependencies I can and can't take advantage of in the code.
Yes.
That same issue here.
Yeah,
So something we can work on figuring.
So the number one goal is to have the semantics of these things clearly defined. And in the case here, the semantics that have been defined so far is that the loops basically have atomic coherence. And if that's not strong enough for some use cases you're thinking of, then we should talk about what those use cases are and why you think they need stronger than atomic coherence.
Okay, so I wanted to talk a little bit about pointers in Regent. The way that we get type safety with Regent is that pointers are explicitly typed on the region that they point into. And this includes even null pointers like the null pointer here. This is going to be a null pointer that explicitly points into a region. And we can do things like allocate pointers inside regions. Our unstructured index spaces are initially empty, which means that you can do things like allocate elements inside of them dynamically. And this is as opposed to, for example, the structured index spaces, which are initially completely allocated. So when you specify a rectangle for a structured index space, you're going to get all of those points available to you immediately, as opposed to an unstructured index space where you have to go allocate those pointers yourself. We can access data stored on a pointer just by accessing the fields with dot syntax. So in this case, we're going to be building some linked list and aligning every element and making that element point to every index in a grid. And then we can do things like use these indices. This is going to be the 2D index in the grid, and we can use that to access the points region, which is, again, a region on that 2D index space. Yeah?
Quick question. What is the no pointer node list mean and new pointer node list?
Yeah.
Why are there all those different things?
Right. So if I go back to the slide on field spaces for just a moment, the reason why, so this first list is an argument to the node field space, right, which is telling it what region that node is allowed to point into. So this is going to be a pointer to a node, which is going to point into the region list. And then the second list is saying what region the pointer itself points into. So for example, you could have a graph with edges, right, where the edges point into a region of nodes, right? If you had a pointer to an edge, right, the pointer itself would be pointing into edges. But the edge would be pointing into the nodes. And so those two regions would be different. Right? So you can use this to build mostly arbitrary pointer data structures, right? With separate regions that point in between them if you want to.
Yeah, I think another way of saying it, that's just standard recursive data type declaration written in a slightly odd syntax because we're doing it inside. We don't have separate syntax for recursive data type declaration. Okay.
Right.
It's just a recursive data type declaration.
Yeah.
You said it already, but what does the region produce? Does it produce source? Does it produce assembly?
OK.
And if it produces source, at what level? Of legion or realm?
Right. So we actually use LLVM to JIT to machine code. We link against the Legion C++ API. Right. So we actually use Clang's parser to parse the Legion C header file. And then we emit calls in LLVM to call to that C API.
So I can't see what region actually did. If you produce intermediate source, I can see what region did, and if I don't like it, I can tweak it, but there's nothing possible.
Right. So you can't modify the source because there is no source. But most of these constructs are fairly one-to-one with the C++ API constructs. We've gone to some effort to make sure that things are straightforward. So generally, if you look at a piece of Regent code, you can understand what C++ code you need to write to do the equivalent thing. You do have to do a little bit more work because you're making up for optimizations that Regent would have done for you automatically. But the constructs are mostly one-to-one.
All right, if I can jump in real quick. Elliot's been focusing so far mostly on the things that do have direct one-to-one mappings with the C++ API. One of the other things that Regent is going to be doing, and Wanchan, are you going to be talking a little bit more about this later, is it also generates good leaf task code. And that's a case where there may be no C++ code with as good performance as the stuff we're generating. So for those reasons, sitting on Clang and an LVM is better in that respect.
Yeah.
So do we have support for more complicated data types like a hash table or a priority queue, or what are your thoughts about that?
So you can certainly build those data structures. The thing that gets tricky when you start doing that is understanding how you partition them.
Right.
Right? And so you will need to think in more detail about exactly what you want the parallelism to be and make sure that you're using a data structure and a partitioning scheme that's going to work for that. And I think we'll cover a little bit more of what that partitioning can look like in the next talk.
Okay. So one small question. Do you have any sort of garbage collection going on here at all, or everything is programmer
So
managed?
let's see here. So we do have this new operator, which is doing dynamic allocation, but everything is allocated inside a region. And so that means that when the region gets deallocated, everything inside of it automatically goes away. So the only garbage collection we would need to do would be on the regions themselves, not on the individual elements. So Legion does have a garbage collector.
I would say, you know, at the source level, you're not doing any. It's all up to the programmer to manage their data by allocating regions and deallocating the regions explicitly. You know, there's going to be some details I'll talk about later about how the runtime deals with physical instances of logical regions that get created in the memory hierarchy. But it's completely orthogonal from, you know, effectively there is no garbage collection here at this level.
Well, so
What about the iSpaces?
No, they're dynamically allocated just like everything else. And it's up to you as the programmer to decide when they get created and destroyed.
Well, so there's no destruction in Regent right now. I think the plan is to have automatic memory management of one form or another. But I think for most things, we can actually do static allocation and deallocation of regions because we understand exactly when those regions are going to live. So I think we can actually insert those destruction calls automatically for you. So I just wanted to talk about a couple of things that we do automatically for leaf tasks. So when we have a loop over a region, we can do things like vectorization of that loop automatically. And this is something that we can do actually better than a C++ compiler because we understand, for example, that X, Y, and Z are going to be disjoint fields. They're distinct fields, and therefore those operations are independent, which gives us a better ability to vectorize loops compared to C++. If you need to, you can require that the compiler does this transformation by adding a little pragma to the top of the loop. It's important to note that this pragma does not have semantics like OpenMP. It's more like specifying W error on your code. So it's a request that if the compiler doesn't do this transformation, it should issue an error, so that if something happens when you port to a new machine or something changes in the compiler, you'll know that your code isn't running the way you want it to. But it's never going to force the compiler to do a transformation that it can't prove is safe. So if you annotate your pointers with restrict, then it might. So these, every field in a region is going to turn into a pointer, right? And if you don't carefully mark all your pointers in C, then the C compiler may or may not be able to prove that they're independent. Yeah. In our experience, the C compiler is mostly pretty good about it. But there are certain cases which it does poorly on. And specifically, for some of the examples that we've done, we've needed to handwrite SSE intrinsics for some of the codes to make sure that they get vectorized. And one of the nice things is with Regent is that it increases sort of the set of things that you can work with an auto vectorizer for before you have to go and write your vector intrinsics by hand, right? So there are always going to be some things that we can't handle. But this is trying to sort of grow the set of things that we can handle with a compiler. And similarly, for certain kinds of kernels, we can actually generate CUDA code automatically as well. So we can generate CUDA code for cases where we have effectively a function which is calling some sequence of loop nests. And for functions which call loops which we would have been able to vectorize, we can automatically generate a CUDA kernel. And then like before, there's another pragma that you can issue at the top of the task if you want to make sure that the compiler throws an error if this isn't going to happen. So just a couple of other things. Since we link to Clang, we actually have the ability to include C headers directly. So we can do things like call printf, call the CMath libraries. And we can also do things like include Legion kernels, which were written for the C++ API, as long as those C++ functions have wrappers which use the C API. So in this case, we've linked some dynamic library which had a Legion kernel written in the original Legion API. And then we just include that and call it, and we've got a couple of helper functions to fish out the various runtime contexts that you need to be able to run your Legion code. And so this gives us the ability to interoperate with effectively arbitrary Legion code in our region applications. Question?
It's a question from me. Elliot, could you spend 30 seconds on why you have to use the C API instead of the C++ API, and why your code looks suspiciously like Lua code?
So, so there's really two questions, right? The first is that we're using Terra. So this is actually an embedded programming language. We've got it embedded inside of Terra. Terra is this sort of two-part programming model. It includes a scripting language called Lua, which gives you the ability, which is just sort of a standard scripting language with functions. And then it embeds inside of that a language called Terra, which is a lot more like C, which gives you the ability to JIT functions. So Regent is implemented as a compiler to Terra, actually. So you could grab the Terra source if you wanted to. But that gets JITted to LLVM. And specifically, we've grabbed Terra's standard library here in order to include those C functions. The second question of why we can't call C++ is more that calling C++ from anything that doesn't look like C++ is hard. We do include the Clang parser, so parsing is not necessarily the issue, but I think the object model is different enough that it's a stretch to try and include those things. But we can do things like metaprogramming, and instead of using templates, we can do them with Lua functions. So this is just the Lua function. It's what you would normally use if you were scripting in the Lua language. But in our context, we can use these functions to take, for example, types or values, and then we can spit out tasks, regent tasks, using the types that we've interpolated from the Lua context. So here, we're going to make a Lua function which generates tasks which increment their arguments. And these tasks are going to operate on some user-defined type T. And then we just call that Lua function with some type to spit out a version of the task that does whatever we want. And so this gives us a much more productive way of doing metaprogramming without needing to do templates. So there are a couple of optimizations that the Regent compiler is doing that you would need to handle yourself if you were programming in C++. So I think it's worth spending a little bit of time talking about what those optimizations are. The first of these optimizations is index launch optimization. So I've given us a timeline of what the program looks like when we have an optimized Regent code. So this is Regent code with all the optimizations turned off. And what we see is that when we go through a for loop of all these B tasks, we have to do a little bit of analysis for each task. We're literally running the program sequentially, and every task gets launched once. So that means that we get 3 analysis boxes for these 3 tasks. That, in general, is going to be O of n in the number of tasks we're going to launch. And that's going to be a problem for scalability as we try to scale up. So the typical thing that we do in Legion is that we turn this into an index-based task launch. This is a special Legion feature, which I've made up some syntax for here. This isn't real Regent syntax because this doesn't exist in Regent. But you would write conceptually this code in Legion C++ in order to shrink those 3 analysis task boxes into 1 analysis box in order to amortize the analysis cost for these tasks that you're going to launch. And this is something that we do automatically in Regent.
I'm sorry. Just a question. Is it, because I'm using index launches in Legion, so is it what is actually being done if you're using the Legion runtime? Is it done like this? There's only 1 analysis?
So if you're using index launches, this
Yes.
is what you will get. Right?
You mean today, this is the current behavior
right.
now?
Yes.
Okay. All
Yes.
right. Okay. Thank you.
So most of our Legion C++ programmers actually start with index launches and never write single task launches because you always want to get this, right? But in Regent, you don't have to think that way, right? You can write whatever code you want, and we automatically transform things into the index launches on your behalf.
So, along the same lines, the user is supposed to express concurrency mainly through partitions of regions. So in this case, the task A, you're running it as a single thread because it's just taking the region R. Whereas if instead of R, if I were to pass on partition P, would the task A also automatically get split up into concurrent tasks?
Yeah.
Okay.
Right.
So the user should express concurrency mainly through partitions, and that's what gets transformed to an index launch.
Right. So the way that you should think about writing your programs is that you want to partition the data so that you can run pieces that are going to be able to run in parallel, right? And then you're going to write for loops, right, like this one, which specify which tasks need which pieces, right? And then the Regent compiler will automatically turn that into an index-based launch, right? If you're a Legion programmer, right? You still think about partitioning, you still think about tasks, but then you write that index-based launch directly instead of going through the Regent language to do it. So there's a second optimization that Regent does automatically on the user's behalf. And to understand this optimization, what we need to understand is that tasks can generally launch arbitrary numbers of subtasks. The Legion runtime doesn't know how many subtasks there are until the task is actually finished executing. And that means that analysis for subsequent tasks can't start until the task has finished. So of course, there are many tasks that aren't ever going to call any subtasks. And the Legion runtime allows users to explicitly mark such tasks as leaf tasks in order to tell the runtime that there aren't going to be any subtasks coming out of those tasks, and the Legion runtime can start its analysis of subsequent tasks right away. It's worth noting that, so of course, the Regent compiler does this automatically for you by scanning the source of each task to determine whether it's a leaf task or not. And one of the interesting things about this optimization is that I've not enabled the index launch optimization in this case. So I'm still doing one analysis box for every single task, but because of this optimization, because the runtime is able to run ahead, I'm still mostly executing these things in parallel. And so that's one of the things which is interesting about this compiler, is that we can actually fail some of the optimization some of the time, and it doesn't impact performance. That each of the optimizations on its own is frequently enough to enable parallelism. So there's one final optimization that you would need to handle yourself if you're programming to the Legion C++ API. And to understand this optimization, notice that tasks can generally run concurrently with their parents, right? Parent tasks generally want to run ahead of the execution to launch subsequent tasks so that Legion runtime can find enough parallel work to fill up all the processors. Generally, those subtasks take regions which were owned by the parent task itself. And that means that the subtask could be reading or writing some data while the parent is also simultaneously accessing it. And that's going to be a data race. So in order to avoid data races, the Legion runtime provides an additional feature called mapping and unmapping, which allows you to explicitly control when the parent has access to subregions. So we're going to unmap a region to effectively say we're going to give up control of the region to child tasks. And then we're going to map the region again when we want access for that data back. And that map operation is going to block in order to ensure that we don't get data races with the child. So by default, the Legion runtime, in the absence of any other calls, is going to insert one of these unmap calls and a map call before and after every single task launch in the system. And that means we're going to serialize effectively everything, especially if we also turned off the index launch optimization, which is the thing that was amortizing the analysis cost before. As the compiler or a smart user, you can issue unmap and map calls before a sequence of tasks, and then only issue a single map call at the very end of a sequence of tasks to make sure that those tasks don't have to block the runtime between every task launch. And one of the nice things about the compiler is that we can do this automatically, and in particular, as a user to the C++ API, this is something the runtime can't really check for you. So if you get it wrong, you're going to have data races in your application. So there are a couple of other optimizations that I don't have much time to talk about. One of the things that you might care about as a user is futures, which represent the values of tasks which haven't completed yet. The rest of these are things that you would not normally, let's see here. So the middle two are actually things that the compiler does, which normally you wouldn't think about in the Legion API. The last two are things for automatically generating kernels, which are things you could do in the C++ API, but you have to write those kernels yourself. So then there are two optimizations that are sort of work in progress that I wanted to just describe quickly to show where the compiler is going to be able to go in the future. So recall, the Legion runtime is doing a dynamic independence analysis that determine where the dependencies are in this dependence graph. Well, this dependence graph is something that we could plausibly compute at compile time. We can essentially build a static version of the dynamic analysis that we do in the runtime. And to the extent that we have good information about what's aliased, we can just feed that information into the runtime so that it doesn't need to compute it dynamically. The advantage of doing this is that we can shrink those analysis boxes. Right? And in this particular example, that didn't make much of a difference because the runtime was already off the critical path. But if you're issuing lots and lots and lots of tasks, or if you're issuing very small tasks, this is going to be important for performance. And this is something that is not impossible to do by hand, but certainly a lot of work to do by hand, and is easy for the compiler to do for you.
It's also worth pointing out that even the compiler only gets a part of the analysis correct. It can just tell the runtime what it knows and then have the runtime fill in the holes. Lots of compilers say have to completely punt if they can't get all their analysis correct. It's like disables all their optimizations. But in this case, we effectively have both the static and the dynamic components, and you can have the compiler has a fallback to rely on in case it can't actually do everything.
How should we express reductions on a region that's partitioned, and how does the region compiler handle that?
So we've got a reduction privilege, which I think Alex showed, but I left out of these slides. So in addition to reads and writes, you can say reduces with some operator on a region. You can also do things like, if you want to reduce to a global value, you can just return each of the sub computations from each task, right? So each task will return a value, and then you can plus equals that into a variable, and the compiler will automatically turn that into operations on futures. Right. So there's one final optimization, and this optimization shows up when we're running on very, very large machines. So one of the issues with launching lots of subtasks from a single node is that we have to stuff all of those subtask launches into the network, and they have to be communicated to all the nodes that are going to run those subtasks. That introduces a latency with each task launch, which is going to rob us of some of the parallelism that we had in the system. You have to run with many more nodes to actually see this happen, but for large runs, this is an issue. And there's a second issue, which is that even with these index-based launches, as they're currently implemented, they still grow slightly with the number of tasks that are being launched. So they're still actually O of n. They're just O of n with a much smaller constant factor because we can do a lot to amortize that analysis cost. The way that we can that we traditionally deal with this in the Legion runtime system is that we split this task into a bunch of long-running tasks. Right? We're going to issue one of these tasks to each node, and then each node is just going to worry about the tasks which have to run on each piece. Right? So it's still going to be doing dynamic analysis. It's still going to be discovering dependencies, but it only needs to think about the dependencies which occur on that subpiece of the computation. But the cost is that the programmer has to be responsible for any communication which happens between those pieces. So you have to issue copies and synchronization whenever there's communication between the pieces. The compiler can automatically find these copies and synchronization by imitating the runtime analysis that the Legion runtime would have done for the dynamic code. So this is actually reusing the analysis that we used for computing static dependencies. We can take that same result and find where the communication is going to cross from one subpiece to another and automatically insert those communication points on behalf of the user. This is actually only one of a couple of ways we're solving this problem, but this is how it's going to be solved in the compiler. So I just want to finish with one point, which is actually getting back to something that we said earlier. This compiler does not stand on its own. It is generating code to the dynamic runtime. And because of that, it actually has a different purpose than a standalone static compiler would have. Instead of going on its own and trying to do everything statically, the goal of the compiler is to improve the efficiency of the dynamic analysis. So we're trying to suck as much of the analysis work as possible into the compiler to make sure that that analysis work can happen efficiently. But in cases where that can't happen because the application is complicated or for whatever reasons, we can still rely on the dynamic analysis, which gives us some flexibility to work with a broader range of applications than we could do with traditional static compilers. And with that, I'll take any questions. This, yeah.
So imagine I have my crusty S3D programmed in Legion, and I'd like to port that to Regent. I had the feeling that's not quite possible to do that piecemeal using your interoperability functionality, but maybe I missed that. Would I be able to do that?
So let's see here. So the thing that you would want, presumably want to do is you would want to start taking tasks one at a time and writing them in Regent. You can actually do that. So this, because we're using LLVM as a JIT, we can use LLVM to spit out a .o file or a shared object, right, which you could link into your Legion C++ application. The trickier part is defining an interface which allows you to call into Regent from the C++. And that's the point at which, if you've been writing purely in the C++ API, now you need to understand how C++ objects get converted into C API equivalents, right, so that you can call those things. And that's not actually so difficult, but it would be a little bit of work. But because everything's still in Legion, it's actually not so difficult, right? So you can, take the tasks one at a time and write them in Regent if you want to, with a little bit of work to handle the differences between the APIs. And this actually goes for things like DSLs as well, right? If you had a DSL that was really great at generating kernels for some specific problem, you might want to use those kernels from that DSL and do the rest of it in C++ or in Regent, right? And you can use that same ability to interoperate to integrate those as well.
Okay, thanks.
I'm going to suggest we take, just in the interest of trying not to get hopelessly behind right at the beginning of the day, let's say like one more question now and we do the rest in the break.
Okay, I guess I get the last question. So you can imagine someone saying that if you are going to embed your language inside of another language anyway, why are you embedding it in Lua instead of embedding it in C++, which everyone's going to be able to use it with?
So one of the advantages of using Lua is that you can do a lot of dynamic sorts of things with it, right? It's very easy to do dynamic code generation in Lua because we've integrated this LLVM JIT so we can JIT whatever code we want, right? If we do source-to-source code in C++, you can certainly pull that code out and run it through LLVM to JIT it. But doing the metaprogramming becomes a lot more difficult, right? Right? Templates sort of get you a certain amount of the distance. They are Turing complete, so you can theoretically do whatever you want with them. But in practice, templates become inefficient when we try to do very difficult things with them, right? And a lot of those things are actually not so difficult in a scripting language. Right? I mean, to some extent, it's a matter of preference, right? Whether you prefer templates or you prefer scripting. But one of the nice things about scripting is that you do have things like user-defined functions that are straightforward to define, and the ability to read files and do standard scripting sorts of things, which are going to be a little bit more difficult in template systems.